So do you have any other questions while we are waiting for your friends?
Biz bu D2 için bir çentikli bir şey kullanıyoruz. Ondan vazgeçtik yoksa?
Well, I'm just lazy. I will not use it. But just keep in mind that it's not the differential of Q, because a function Q just doesn't exist. Other questions? So let's continue driving our Maxwell relations. You see, we had already derived two of them. One, we start with du is equal to TdS minus PdV, which told us that derivative of temperature with respect to volume at constant entropy is equal to minus the derivative of pressure with respect to entropy at constant volume. Well, if you look at this relation, basically, this coefficient, its derivative with respect to this one, is equal to the derivative of this coefficient with its sign with respect to this one. That's nothing but the equality of the second derivatives. And then we said we defined the u minus ts, this was minus sdt minus pdv, which told me that, just basically using the same thing, the derivative of this one with respect to this parameter, minus ds by dv at constant temperature, this is equal to the derivative of this coefficient minus derivative of p with respect to this variable. Again, it's just the fact that if you have a function, it's the second derivative with respect to two of its arguments, you can just change their order and they should still be equal. Well, I can do mainly the same trick. By the way, this trick going from u to u minus ts is so-called the Legendre transform. If you have taken analytical mechanics, basically you do the same thing in analytical mechanics to go from Lagrangian to Hamiltonian. Well, let's continue. I can do the same thing for u plus pv. This will be equal to TdS plus VdP, which will tell me that the derivative of temperature with respect to pressure at constant entropy, you see this is during an adiabatic process, this is equal to the derivative of volume with respect to entropy at constant pressure. And finally, the differential of u plus pv minus ts is minus sdt plus vdp, which tells me that derivative of entropy with respect to pressure at constant temperature with the minus sign, this is equal to derivative of volume with respect to temperature at constant pressure. So these are the four Maxwell's equations of thermodynamics. Well, one thing to keep in mind, let's look at this one. Now, by making these tricks, writing TdS as the differential of t times s minus sdt, etc., it allows me to treat s or t as my independent variable. Similarly, p or v as my independent variable. So these are so-called my conjugate variables. And if you look at the Maxwell-Rogers relations, what they do is it just allows me to relate the derivative of one of the conjugate variables in a pair with respect to another one of another conjugate variable in another pair. So if you look at this one, for example, it's the derivative of S with respect to P. It is related to derivative of V with respect to T. They don't relate the derivative of one of the conjugate variables to the other conjugate variable. And typically, usually they have special names. For example, let's look at TdS, S and T. What is the derivative of the entropy with respect to temperature? Keeping something constant. You see, when I tell you about the process, that will tell you what you are keeping constant. You can look at this derivative. I don't know if you want, you keep volume constant or the pressure constant or the chemical potential constant, etc. That the process will tell you what x is. Now, usually what we do in these cases, this is 1 over t times T ds by dt. This is 1 over t dq by dt. During this process, x. Let me also put this small bar on d, so that it's not the derivative of a function. Well, what is this? It is the heat, the ratio in fact, the heat given to the system to increase its temperature by 1 unit. Well, that is what we call the heat capacity of the system. So if you want to know ds by dt, keeping something constant, this is nothing but 1 over the temperature times the heat capacity of that process. You can talk about the heat capacity at constant volume, the heat capacity at constant pressure, etc. In fact, you can actually prove that in PV to the gamma is constant in an adiabatic process. Gamma is actually Cp over Cv for a general gas. And well, you will probably have a homework for that. This PV to the gamma is equal to constant in an adiabatic process if PV is equal to NKT. If this equation is satisfied, then PV to some constant is constant, and that gamma depends on the kind of the ideal gas. We will see that PV is equal to NKT is quite general. And the definition of an ideal gas is not very restrictive. You have many different gases which behave like the ideal gas, but they have different specific heat at constant pressure, the specific heat at constant volume, and they have different gammas. So any questions up to here? And let me also now mention the third law of thermodynamics. Oh, before that, well, some common definitions will be the heat capacity. There is also the specific heat. which is usually shown as small c. It is the capital C divided by the number of particles. The amount, well, you can talk about specific heat per gram, specific heat per particle, the specific heat per whatever you want. And then there is the compressibility. Well, here we talk about the derivative of the entropy with respect to temperature. Well, another conjugate pair is P and V. So how much the volume changes, volume of an object, if you change the pressure that you apply. Well, this is compressibility is usually defined as per volume. And since this is a negative number, we define the compressibility to be positive. And again, here you have the whatever, you can talk about the compressibilities for various processes. And this is denoted as kappa of x. And more or less, you can express every other thermodynamic derivative in terms of equation of state, the specific heat, or the compressibility. Now, you see, the second law, in order to talk about the entropy, we looked at the differences in the entropy. So this is the difference in the entropy between two states of the system. It allows me to determine the entropy once I know the entropy of a reference state of the system, but it doesn't tell me what is the entropy of that reference state. Well, the third law basically specifies that number. So the third law tells me that the entropy at T equal to 0, other variables, is 0. So it fixes the constant over here. You see, we derive the entropy of the ideal gas. You see, this is the entropy of the ideal gas. Just using thermodynamics, we could determine its form using the equation of state. But we couldn't determine what that constant is. So what is that constant if you use the third law of thermodynamics?
Sorry, I don't understand.
Yeah, you say
what is the statement of the third law?
That the entropy at 0 Kelvin is 0 for every system.
Minus NK. Minus NK.
What was ln 0? I don't remember it numerically.
Infinite, minus infinite. Logarithm of 1 is 0. Well, this basically tells us that ideal gas does not exist at very low temperatures. Now, we will see what the gas becomes. We will see that whether the gas is made up of fermions or bosons, its behavior will be completely different. But the third law still holds. Well, when we start the statistical mechanics, we will see how the third law arises, and we will also see cases where it's violated.
And what are the lower limits that we consider for an ideal gas, for a temperature?
We will see. We will derive it.
So we're going to have another definition for the entropy at
Yes.
0. Or very close.
Well, the entropy at 0 temperature will be 0.
But if it's higher?
Well, you see, okay, so let me just give you a hint. S is k times the logarithm of number of available states.
Microstates? Okay.
So at 0 t equal to 0, the system is in the ground state. The question is how many ground states a quantum mechanical system can have. usually small. Logarithm of 1 is 0, so the entropy at 0 is 0. If you have symmetries, then in that case you might have more than one ground state, which is also not true, by the way, but let's say that if it has more than one ground state, in that case the entropy at 0 temperature is non-zero.
And the third law has no stipulations on it, right? Like closed system or isolated system.
Hmm?
The third law has no qualifiers. Like, so for any system, it holds, right? Not just for isolated systems.
No, for any system, the entropy at 0 is 0. That's the third law. Well, what are some consequences? Let's say, let me put some variable over there. X can be the pressure, it can be the volume, but whichever one you prefer. This will be equal to this. The third law tells me that as temperature goes to 0, this will be some coefficient that can depend on the other variables, but then t to the power some power, so that it goes to 0. This is how it will behave at t equal to 0. Let's look at specific heats. Well, the specific heat, we defined it as T times del S over del T, keeping the other variables X constant. Well, this will be delta times A of X times T to the delta as T goes to 0. This also goes to 0. So the third law basically tells us that any specific heat also goes to 0. Now, what was the specific heat? It was dq by dt. Well, let's see what we can say. If we extract some heat, the temperature will change very fast. Basically, it also tells, if I can manage to extract any heat from a system, its temperature will change very fast. But let's see, how can I extract heat from a given system? Yeah, by putting it in contact with a colder one. Well, if the system is already very cold, even if I extract a very small amount of heat, its temperature will just go below the other colder reservoir. Well, which basically tells me that I won't be able to extract too much heat from the system. It will become very difficult to extract heat from the system. And in fact, you have probably heard that T equal to 0 is not attainable. You cannot reach absolute 0. Well, basically what happens is, if you would like to create a process in which eventually you would reach the system gets colder and colder, it takes you infinite amount of steps to go to the 0 temperature. Basically, that is why we say that T equal to 0 is not achievable. It's based mainly the ground state. So ground state, there is nothing being in the ground state. No, 0 point energy is still ground state. You see, T equal to 0 doesn't mean no energy. T equal to 0 basically means that your system is in the ground state. If you have a macroscopic system, if you can put it in a ground state, then it is 0 Kelvin.
I don't understand. A quantum field is a collection of harmonic oscillators.
Okay.
And the ground state is the ground state of many coupled harmonic oscillators, which has a 0 point energy.
Okay.
So-
Energy is not a problem. Can you actually put 10 to the power 20 particles, all of them in the ground state?
Bosons?
Whatever particle you want to
Bosons
imagine.
included, right?
Bosons included, fermions included.
You could put bosons in a...
Can you put all of them in the ground state? We'll start. I mean, you can put some of your particles in the ground state, but not all of them.
In a BEC, in an ultra cold, in Bose-Einstein condensate, isn't everything in the ground state?
No. Only at T equal to 0, everything is in the ground state. At higher temperatures, part of it is in the ground state, part of it is not in the ground state. Yes, Carl.
So what about like we put an atom in the ground state, so and the system is only that atom, is it like zero temperature?
Okay, fine. So what's the problem?
I thought like it's not attainable, so.
Well, we are talking about statistical systems.
Okay, sorry.
So, I mean, if you see, these laws are valid only for a macroscopic number of systems. If you are talking about one particle, you will get violations of these laws. Or few degrees of freedom, you will have violations of these laws. You will have, for few systems, you will see energy being transferred from low temperature to high temperature, and the entropy increasing, decreasing spontaneously, because basically the derivations are not valid in those cases. So whenever you see some kind of a violation of these thermodynamic laws, just ask, the first thing you should ask yourself is the system you are considering a statistically significant system, or just a few degree system? For example, those who are working on quantum gravity, some of them say that the increase of entropy is a fundamental law. Well, what's the relevance? As your friend had mentioned, the vacuum is filled with fields. It's not empty. It's all filled with fields, and if you look at different regions of the space, you have different degrees of freedom, and you can still talk about the entropy of that system. And some people even speculate that it is the entanglement which creates space in order to increase the entropy, etc. There's all those fantastic hypotheses. There's no fixed theory yet, but there are just some weird ideas.
Can we talk about the existence of kinetic energy for t=0 not being possible?
Sure. No, you see, as your friend was also probably stuck there. T=0 does not imply the kinetic energy is equal to 0. For example, as your friend pointed out, the harmonic oscillators have 0-point energy in their ground state. But if you could put all your harmonic oscillators in a macroscopic system in the ground state, even if they have kinetic energy and potential energy, they have 0-point energy, their entropy would be 0. But you cannot create such a physical system, because it will take you infinitely long to extract all the excitation energy.
And I think these are just macroscopic properties like temperature. Can we even talk about, in the same sense, temperature for particles?
Well, you see, I can always talk about those things, but I should be careful. What are the fluctuations? What are the variations? Variations would be large. And the probability, well, in the first lecture, for example, I said that the probability of entropy decreasing is 0. It doesn't mean it will not happen, but its probability is still 0. Now we can ask, what do you mean by probability being 0, but meaning that it might still happen? Well, let me ask you this question. If you pick up a random number between 0 and 1, what is the probability that it will be just 0.123? A random real number.
Close to 0.
It will be exactly 0, because that is just one real number among infinitely many real numbers, so the probability is practically 0. But in any case, the question doesn't really make too much sense anyway. But we will still talk about cases where the probability is 1. Although we will be talking about different possible outcomes, we will say that the probability of entropy increase is 1. There are other possible outcomes, but you won't see them, you won't be observing them. Other questions? Okay. So, well, the basic question is, let's see. We have all these Maxwell relations. We can relate the various thermodynamic properties to other thermodynamic potentials, etc. So, for example, if you can calculate F, we said that dF was equal to minus SdT minus PdV. If you can somehow calculate F as a function of temperature and volume, well, basically we know everything else. Well, the entropy is the derivative of the free energy with respect to temperature at constant volume. The pressure of the system is minus the derivative of free energy with respect to volume at constant temperature. And well, I also would like to know what the energy of the system is. The energy of the system will be, remember the free energy was E minus Ts. So energy is free energy plus T times S. Well, I know the free energy. I know what S is. It is minus the derivative of free energy with respect to temperature. So once I know the free energy, I know all these. Well, let me also try to simplify this a bit. Let me take T squared out. This is F over T squared minus 1 over T derivative of F with respect to T. T squared times F times, well, let me also take the minus sign out. F times the derivative with respect to temperature, 1 over T, well, at constant volume, plus 1 over T times the derivative of free energy with respect to temperature at constant volume. So if you know the free energy, then the total internal energy is temperature squared times the derivative with respect to temperature of free energy divided by T at constant volume, etc. So you can just derive whatever you are interested in. Once you know the expression of the free energy, you can derive all the other thermodynamic quantities. And in fact, what we will be dealing with in statistical mechanics is how can we calculate these thermodynamic properties like the free energy or the entropy or the other. We will be talking about various free energies. Because once we know them, we know everything else. Well, let me also, before leaving thermodynamics, let me also mention some other terms in this expansion. For example, we might be interested in systems where the number is also not fixed. Then we can ask the question, how much the energy of the system changes as I change the number of particles? So I can add to this something proportional to dN. And that proportionality constant is called the chemical potential. Well, number is easier to measure than the chemical potential, but theoretically we will see that especially when we are looking at fermions and bosons, it's easier to deal with the chemical potential than the total number. And of course, just as we did before, you can say that the chemical potential is du by dN, assuming S and V to be constant. And, well, you can still derive many Maxwell relations involving the chemical potential. For example, the derivative of the chemical potential with respect to volume is mu and n is another conjugate pair. Well, derivative of mu with respect to v will be equal to the derivative of p, well, with the minus sign, with respect to n. All the other variables being constant. So this is s and n. This is S and V. And well, you can work out all the other Maxwell relations. You can imagine a system in a magnetic field and then ask yourself the question, how much the energy changes if you change the magnetic field? Well, that is That's the magnetization of the system. Yeah, of course, you can write the same thing for the free energy. If you like, you can put an electric field, then it will be the electric dipole moment of your system, etc. And again, the question will be basically reduced to calculating the free, and the question that we will ask in statistical physics is, what is the expression of the free energy in the presence of a magnetic field, in the presence of an electric field, when the number of particles change is allowed to change, etc.
Y minus for magnetization.
Do you remember the expression?
Yes.
That's why. You could have avoided that minus sign, but then you won't be able to. If you wanted to relate it to the magnetization of individual atoms, you will always end up having an additional minus sign. And or if for a solid object, well, basically, we use both this and this. Any other questions? Well, let me also talk about the extensive quantities and the intensive parameters. And let's end the lecture today. Well, in fact, if you look at our conjugate pairs, mu and T, S, P, V. Now let me take a system with a given pressure, volume V. Let me take an identical system, and also N. Let me take an identical system with the same pressure, same volume, same number, and combine these two systems. So at the end of the day, I will have a larger system. What is the number of particles in this system? 2n. What's the total volume of these systems? 2v. What is the pressure of this system? It's P. You see, there are these quantities like P over here, which doesn't change if I change the size of the system. So these are called our intensive parameters. P is an intensive parameter. Mu is an intensive parameter. T is an intensive parameter. They do not change if I double my system. Plus, there are other parameters like V and S. These are the extensive parameters. These are the things that, if you double your system, extensive parameters, they should be doubled. Intensive parameters, they should not change. If you triple your system, again, extensive parameters should triple. Intensive parameters should not change. Well, this brings some restraints on our functions, some other relations. Let's look at the energy. Well, in fact, rather than starting from energy, let me look at another one. U minus Ts plus PV. This will be minus S dt plus V dP plus mu dN. Let me call this G. Well, G, if I write it as a function of temperature, pressure, and N, Well, if I just take the derivative with respect to one, keeping the others rest, fixed, it will give me the entropy, volume, and the chemical potential. Well, this is an extensive property, right? Because U is extensive, S is extensive, T is intensive, so if I double my system, T doesn't change, gets multiplied by 2, so T times S is multiplied by 2. Similarly for PV, if I double my system, pressure doesn't change, volume gets multiplied by 2, so PV, all the terms appearing in the definition of G, if I double my system, they are doubled. So G is doubled by itself. But you see, that already tells me that this function has to be n times some function of temperature and pressure. Otherwise, I cannot have this doubling property. Now, what is the derivative of G with respect to n at constant temperature and pressure? If you look at this definition over here. In terms of S, V, and mu, what is that derivative of G with respect to n? Hmm? No, well, you see, look at this relation first. It's just mu. Well, as you pointed out, if you look at the last relation that I wrote, the definition, this is G. So G is nothing but the chemical potential as a function of temperature and pressure. So G is mu as a function of temperature and pressure times n. But this is nothing but U minus Ts plus PV. So I already have another relationship. U is equal to Ts minus PV plus mu n. Again, this is valid for every macroscopic system. And the only thing I use here is the existence of these functions. There are such state functions, and that U, S, V, and N, they are all extensive quantities. Well, basically the rest of thermodynamics is just playing with the derivatives and using these relationships that you derive. And similarly, free energy, which we defined as U minus Ts, which is minus PV plus mu n, etc. So any last questions?
Any book recommendations for thermodynamics?
A tough question, no. Well, if you would like to understand the fundamental, no, Rife is statistical mechanics, no.
Is the first book, undergraduate book, okay?
430?
Yeah.
What do you use there?
I don't know what they use now.
Okay, that's okay. I mean, do you expect me to say, oh, it's not okay, it's a
No, it's
nonsense book?
It's applicable for this course.
It was Schroeder.
You see, there are many books, whichever one you like.
Okay.
You see, some books will be, you like those books. I personally couldn't find any statistical mechanics books that I like. I don't like Path3. But it's better than the other options. Okay, so let's end the lecture today. Next week I will not be here, there won't be any lecture. The following week we will again have 4 hours and we will start statistical mechanics. Okay, so see you the following week.